Hello and good afternoon, and thanks for coming out. My name's Peter Karp. I'm a staff engineer at BuzzFeed, and I'm going to be talking about the use of Redis as a job cache in an auto-scaling distributed video rendering pipeline. It's going to be pretty exciting, and what is going to make this talk a little bit different is I'm going to show some of the evolution of how Redis ended up in this workflow. So BuzzFeed creates about 100 hours of video content a week. Many of the video production tasks are repetitive and tedious to do manually. So of course, as an engineer, I'm looking for ways to automate that. That includes things like captions, adding overlay text to videos, for example, for translation work or localization. In the case of BuzzFeed, we want to be able to insert ads into videos, and there are other services that require us to insert just several seconds of black content so they can insert their ads into it. We're also interested in making use of our extensive back catalog, so we want to have compilations of related videos. And we also may need to do cut downs, which are videos that are similar but different for each of the different video platforms that we distribute on. And to support some of this work, we created a short-form video editing tool called Vidder. And I'm going to get a chance to show you that later. So rendering video is slow and very memory intensive. So this talk is going to show how we iterated through the development process of building a prototype rendering engine as a back-end on a web server. We then went to production with a version 1, which was running in our microservice environment. And then we started to see over the course of 6 months or so, as our users started creating more complicated videos, that we needed to look into distributing the process across multiple servers and introduce auto-scaling into that as well. So you could imagine that once you start decomposing these large jobs into smaller jobs, this is where Redis came in, and we were going to run these jobs on multiple microservers, and they would be coordinated by this job cache running in Redis. So the rendering engine is called Stitcher, and we're going to be talking about version 2. What it does is assembles video clips, images, and text together into a video using a simple JSON syntax, which is the Stitcher SL, the schema language. It's going to allow you to overlay text, images, and video, join that video together, and also do some trimming, cropping, resizing, and positioning of different content. We're also able to add captions that are rendered between some start and end time. So the tech stack is Python 3.6, a third-party package called moviepy, the ever-popular ffmpeg, Marshmallow for object serialization, and of course Redis. The requirements for our job cache were not that difficult. We're building for an internal tool with a fairly small user base of internal developers, internal content creators. But what we do need to do is we need to have access to the job info throughout the distributed microservice environment. We want to persist the rendering jobs while jobs are running, but long-term persistence is absolutely not necessary. We can just remove all that information once the job is finished. So shooting video itself is a pretty easy process. You basically see people all the time just pointing their camera at things and shooting many seconds of content. But editing videos together is much more complicated. If you were shooting video or film back in the day, you would actually be cutting physical media. And even today with digital, the interfaces are very complicated. So at BuzzFeed, we built a custom editing tool called Vidder. And the goal here was to allow our content creators who are normally writing content for the site to have the option of creating video content as well. It also allowed, in this case, to be able to actually trim video content fairly simply. So the Stitcher schema language describes how to combine media clips into a video. And there are 3 types of clip types. There's video, image, and text. And then there are the way you schedule these different bits of media. You can either sequence them together or schedule them in parallel, which basically means compositing them over one another as overlays. So examples of the clips for video in Boulder, the required fields. So you want to be able to describe that the clip is a video, and you give it the source at some URL or a file name. And similarly for an image, however, the image also has an additional required key called duration to tell you how long that image will be displayed for. And similarly for text. The optional parameters are obviously not necessary, but they are configurable nonetheless. So the schedules that I mentioned, there are 2 types. There's the sequence and the parallel, and that's what these look like. For a sequential schedule, you just give it a list of the clips that you want to sequence together. And similarly, for the parallel schedules, you give the list of clips, but these are going to be overlaid on top of one another in some fashion. Now, the big benefit of schedules is that they can also be nested within other schedules, so you can have arbitrary complexity. And in this example, I'm showing a sequence of 2 schedules, and then inside of that sequence are 2 parallel clips. Sorry, 2 parallel schedules that are themselves including a piece of video and a piece of text, and these will be joined together. And what this is showing here is what the output of that schema language would have produced. It produces 2 composited schedules, and they're going to be joined together. So as I mentioned at the beginning, I wanted to talk about the evolution of the architecture that we were using. We started with a prototype, just a proof of concept that would do a rendering in the back end of an actual of a single web server. As we moved into production, we split that out into into 2 dedicated services. One that would validate the payload, and the other that would render the payload. And then finally, with version 2, we created a distributed system with multiprocessing and autoscaling. We would decompose the payload into small tasks, and we would run the jobs on autoscaling microservice, of course coordinated with a Redis job cache. So for Stitcher 0.1, the prototype, it was basically, as I mentioned, a web server, and on the back end was the rendering engine and an S3 bucket for the media and the output. And a simple post call would send the command to the API interface. As a demo, we created something called Video Slot Machine. This was a Hack Week project to demonstrate the capabilities and the potential of programming the ability to create videos on the fly. So the slot machine had 25 different search terms on each of the wheels, and then each of those search terms might return 50 videos per item. And then the numbers represented offsets into each video, and then how long of a duration you would take each clip for. It was just a fun way to demonstrate the variety of automated video content creation. So Stitcher v1 was production ready, and we had the front end was going to use Vidder as an editing tool, but most important is that we had separate servers for handling the API requests and the rendering. We split those out. And this shows the kind of the architecture of that. The Vidder on the front end, Media Stitcher API receiving the requests, sending a message into our message queue, and then the rendering engine processing that payload. Again, that's on a single server. And the S3 bucket was there for the media storage, as well as the final output was written to S3. So diving into the renderer, there would be the event handler that gets the message off of the queue. It validates the input, that's the Stitcher schema language. There were message timeout limits, and so we needed to be able to constantly send basically a heartbeat back to the queue to let them know that we're still working, and that's what the touch command is for. But running in a separate process launched at the startup of the payload receipt was the rendering engine. When that finished rendering the video, it would write it to S3. It would indicate completion. That would send the message back to the message queue, and also make a call to the webhook to let the caller know that the job has been finished. But we were hitting some serious limits with this architecture. Almost immediately, one of our content creators wanted to create a very long video with numerous clips, in this example from 13 Ellen Show moments. And what we started to see was the requirement of rendering all of those clips together was taking a lot of memory, and it was also starting to hit some of the timeouts that our message queue was imposing on us at 15 minutes. And that's when we had to consider a different way of processing the video. So we approached it by distributing the rendering effort across multiple servers, and again, coordinating that task, coordinating that effort through the Redis job cache that we created. As a result, we had an enhanced performance because we were then able to auto-scale each of the rendering engines in our microservice system. And suddenly larger projects were possible in Vidder. We were able to take advantage of the independence between what we call the cells of in the Vidder project. And those are basically self-contained periods of time where there's a single clip of video and the overlay of text. But we were also, as a result of this, we were able to handle captions and audio tracks, which previously were taking too much time to process on the single instance. So a little additional complexity, but we'll step through this each link at a time. So on the back end of Vidder, they would make a call with the Stitcher schema language to the API. A message is sent to the message queue with the payload, and that's received by the service called Media Stitcher. It creates an entry in the job cache that there's a job with multiple, that will require multiple engines to render. And in 5A through 5D, each of those renderers receives the message with its piece of the task that needs to be rendered. Each of those services is pulling down media, different videos that are already on the S3 bucket, and also writing their intermediate results to another S3 bucket at number 7 there. At the point where each renderer finishes, it goes back to the job cache and just makes a note that it completed its rendering job. The last one in there, it checks to see, am I the last server to complete? It then sends a message back to the queue that's picked up by Media Stitcher to then do an assembly of all of the individual pieces of rendered content. So in step 9 and 10, that's showing Stitcher pulling down all of those individual pieces and stitching them together. And this is where ffmpeg does a tremendous job as well, joining that type of content together very quickly. And then it pushes back the finished assembled content to S3. And finally, it calls the client webhook, and the client can then report to the user that the video is ready. As we saw before, it's the renderer is the same as we'd seen earlier, minus the necessity to call the webhook here. That's done back in the API. But and it's also why we're able to scale this thing, because each one of these now is doing the exact same work. So what I'm showing here, we use Datadog for monitoring our services, and this is showing in the upper chart the start and end time of from the time that the API is called to the time that all the work is finished. We see that there is some memory use, and we're showing the percentage in use. More importantly is the CPU usage across all of the rendering engines. If there are insufficient number of servers running, we do the auto scale at that point that's triggered off of the CPU usage. And so in this example here, we're scaling from less than 5 servers to, I think, 12 servers. And they ramp up relatively quickly, allowing us to gain the advantage of having more servers on the job. And they decline when they see that there's no more CPU usage going on. So I want to go through the steps of the Redis job cache. I will say, compared to a lot of the other talks that I've seen here today in the use of Redis, this is a very simple use case, but it really solved the problems that we had, and it was great to work with, to set it up as quickly as we did. So we first initialized the cache for a new job, and we add a unique job ID to the jobs set using the sadd command. We also add a list of task status using the rpush. So we have a key called status job ID, and we push that out there. So that is a list of all the tasks. Then as the renderers complete their work, each of them is going back to that list and changing the status to either success or error, and that there is a check made that if all the tasks are set, and that we use the lrange command. And finally, we can clear that out on completion using the srem command. And here's an example of what some of that looks during a running job. That job's set, in this case, there's nothing running and it's empty. If there's a single job running in our environment, then that job list includes this single value that has the job ID, the overall size of the job, and then the status list, which shows the status. All of them are started, they're ready to go, and so started is 4 also. And once the jobs start completing, each of those is setting its task to success. So we show here that the size is obviously still 4, but the started is only 2. So in comparison between V1 and V2, I don't think I'd be standing up here if this wasn't a significant improvement in performance. I'll just point out that in V1, we had to do sequential processing of the entire video from start to end. All the cells were processed on a single instance. We had to do a kind of a workaround where we started batching 8 cells at a time to try to keep the memory load low enough. We were running in a 2 gig instance, which it was a limit set by our microservice environment. But I think as an engineer, it's always good to work with as little memory as necessary. And then finally, there were some long videos that hit this 15-minute message timeout. Again, this was a limit of our message queue. But we improved on all of that using the V2 rendering approach. We had fast parallel processing. A single Vidder cell would be processed on each instance. There was no more special casing of grouping cells together. We were able to render on 1 gig instances because we were dealing with a lot less content. So single cells were unlikely to hit any kind of memory limit or timeout limits. And we've even gone further where we can start to subdivide even jobs that are several seconds long into multiple jobs that are 10 seconds, let's say. So if you have a 30-second cell, cut that up into 3 cells of 10 and run those in a distributed way. The order of rendering doesn't matter as long as you assemble them correctly at the end. And just some of the improvement numbers that we were seeing with some examples. This 15-cell, almost 6-minute video had a 2.6 time improvement. And that was pretty impressive for this. So the automated and assisted editing can increase productivity in a high-volume production environment. And scaling video rendering tasks in a high-volume environment is challenging. Stitcher made that easier for us, and Redis really made it faster and possible. So my slides are available here. I think I have time. I can show a little bit of Vidder. So this is Vidder, and I created this, just yesterday. And I think I'm going to just go directly to the video that this generated. So this is demonstrating the overlay, the compositing of text, images, and an icon with some dynamic animation, panning and zooming on the content. There is also an audio track that we laid down, but that's another channel that we were also able to support. And this is just from yesterday. And, well, thank you all for coming to my talk. So are there any questions?
I have one, actually. Were they able to complete the 13 best Ellen Show moments?
I'm sorry.
Were they able to complete the 13 best Ellen Show moments?
Absolutely.
All right.
Yeah.
Anybody else?
Okay.
All right. Thank you.